brief overview of HyperWorks and our solvers, followed by my co-presenter Dave Corson going over AcuSolve specific FSI or fluid structure interaction capabilities, and also giving us a demonstration of AcuSolve and Radios for FSI. We'll follow up with a few summary slides and end up with Q&A session. So we'll continue on with our introduction to the HyperWorks Analysis Suite. The suite, which is based on a patented token-based licensing system, includes 4 main components: modeling in Viz, which is labeled pre and post in this slide, process and data management, solvers, which includes AcuSolve for CFD, Radios for structural mechanics, and MotionSolve for MBD, and optimization. And also on the right-hand side, you'll see a Partner Alliance Solutions box, and that includes almost 50 additional third-party applications, again, all enabled by the HyperWorks token-based licensing system. Now let's talk about how we can solve multi-physics tasks. We can put all the tools in one box, label them with the same name, and solve everything simultaneously, but this would cause lots of overhead and compromising on our individual solutions. So our solution is different, and we call this smart multiphysics. What we mean by this is that we make sure that our codes can talk to each other and exchange data on different levels. How AcuSolve, say, would exchange data with Radios for FSI is going to be different than how it would exchange data with MotionSolve for doing a coupled multi-body dynamics simulation. So different levels could be as deep as writing the equation solver, or by doing co-simulation, or just up on the modeling level. With this approach, we make sure that we provide solutions to our customers that address their needs and can solve large-scale multi-physics problems with the scalability, quality, and robustness that is known from our single physics solutions. Now, I just want to make note that today's presentation is focused on AcuSolve for the fluid dynamics and Radios for the structural mechanics. We also have some unique capabilities very tightly coupled inside the Radios code. Radios has an explicit CFD solver technology based on either an ALE method, arbitrary Lagrange Eulerian, SPH for smooth particle hydrodynamics, and recently an FVM, finite volume method capability, again in an explicit formulation, whereas AcuSolve is implicit. And I just have some animations here. On the left-hand side is fuel tank sloshing. On the right-hand side is aircraft ditching. And on the lower right, the animation is a airbag deploying. So there are some technologies where explicit CFD codes have proven to be very, very robust. But we're going to limit this presentation today to AcuSolve for the CFD solution and Radios for the structural solution. And we'll discuss the different levels of coupling. So I'm now going to hand it off to my co-presenter, Dave Corson, who will talk about an overview of AcuSolve, its FSI capabilities, and go on into a demonstration.
Okay, thank you, Simone. So as Steve mentioned, there are a number of different types of FSI capabilities that we contain within our tools. So we're going to focus on the capabilities available within AcuSolve. And I want to start out by just introducing some of the technology, and then we'll talk in a little bit more detail about some of the different options. And then we'll go through a demonstration case where we actually use one of these technologies and apply it to solve a real-world problem. So just to give an overview of what you should expect to learn from this demo, I want to talk about the basic multiphysics capabilities of AcuSolve, and I have these divided into a few different areas. One is rigid body motion, one is practical fluid structure interaction, or PFSI as we call it, and another one is directly coupled fluid structure interaction, or DCFSI. We're going to talk about each of these 3 different approaches, and we're going to talk about when to use each type of modeling. And more specifically, we're really going to focus on the PFSI and the DCFSI, and we're going to talk about the benefits of each technique. The rigid body motion is of course, a form of multiphysics, but we generally don't consider it to be fluid structure interaction. So what we're really going to focus on in this webinar is the fluid structure interaction side of things, which is the PFSI and DCFSI. In addition to that, we're going to learn a little bit about the hands-on capability, or the hands-on exercises required to set up these types of simulations. So we're going to be using AcuConsole to set up our simulation, and we're going to look at some of the basic CAD associativity capabilities that we have within AcuConsole. And we're also going to learn about some of the interoperability between AcuSolve and Radios, as we'll be using both packages for this. As we go through my slides, you'll see a number of different images and some animations. And these are really just intended to convey a sense of the different application areas where we've applied our FSI technology. It's by no means a complete list or a complete showing of the areas where we've applied our technology, but rather just some animations and images that are fairly recent work, and we're going to be showing them. So let's start talking about the different types of multiphysics that AcuSolve supports. The first type that I want to talk about here is rigid body dynamics coupling. AcuSolve does have a 6 degree of freedom rigid body solver embedded within it. There's no limit to the number of individual rigid bodies that you can solve for, but there is a limitation that the rigid bodies can't be interacting. So in other words, we can't have linkages between all these different rigid bodies that are present. That would fall under the category of a multi-body dynamics solver, and our solver motion solve, of course, is tailored specifically towards that application. So AcuSolve isn't necessarily intended to do that type of a simulation, but rather it's intended for unconnected rigid bodies. So when would you use this type of a technology? Well, there's a lot of different application areas for this, and I think one of the most common areas is these floating platforms that appear out in the ocean as part of the oil industry, or now they're even trying to be developed for the wind power industry. Boats, so really anything that's bobbing around under the action of waves and somewhere out in the sea. So in those applications, it is multiphysics because we have the fluid interacting with this rigid body and forcing it to undergo motion. But it's not fluid structure interaction because we're not actually deforming the structure. So we don't, we're not really interested in whether the hull deforms or whether these floating platforms deform. We're just interested in the bulk rigid body motion of the object. So that's some of the common application areas. Now, of course, there is some overlap between these different technology areas, or I'm sorry, different technologies for multiphysics that we're talking about here. We can certainly simulate a rigid body motion using a full fluid structure interaction simulation. But there's additional overhead that comes along with that. So the rigid body dynamics really covers a fairly broad class of problems where we're just interested in the bulk motion of some object and not necessarily interested in any deformation of that structure. So on this slide, I have a couple of animation, or an animation and a couple of images from the offshore oil industry. So we have a floating platform on the bottom left that's kind of bobbing around in the ocean. And on the right-hand side, we have two examples of straight risers and faired risers. And these are really just pipes that extend up out of the ocean and are connected to these floating platforms. And those pipes undergo motion due to the subsea currents. The next type of multiphysics that I'd like to discuss is what we call practical fluid structure interaction, or PFSI. And using this technology, this is a full fluid structure interaction. We are solving for the deformation of the structure as a result of the loading from the fluid. And this technique utilizes AcuSolve exclusively for performing the full analysis. So AcuSolve solves for the fluid as well as the structure at runtime. So there's no type of coupling between AcuSolve and any type of an external package. There's no communication present between AcuSolve and any other package. Everything is done completely internal within AcuSolve. So how do we do it? Well, we base it on a modal superposition approach. So the way that we would set up one of these types of simulations is that we would first perform a modal analysis using our favorite structural tool. So we would perform our modal analysis using Radios. And then we would import those mode shapes and eigenvectors, and eigenvalues into AcuSolve and transfer that information to the fluid model. And once that information is in our fluid model, AcuSolve will compute the modal participation factors of each mode based on the fluid loading. And then, based on those modal participation factors, we can compute the displacement of the structure and then just superimpose all the displacements for each mode and come up with our displaced shape. So this technique is extremely robust, it's extremely fast, and it works extremely well for a very broad class of problems. And here you see a number of applications. On the right-hand side, we see a reed valve that's being opened under the increasing pressure from the flow. And then when the pressure decreases, that reed valve closes and pinches off the flow. On the left-hand side, we're seeing an example of nuclear fuel plates that are being separated due to a flow imbalance. So these are both applications where we've had great success using this PFSI technology. Now, the limitations of this technique are that because we're using a modal superposition technique, we're really limited to linear structural displacements. So if there's any type of a massive nonlinearity, meaning we have a strongly nonlinear material model, or we have large number or a large amount of contact present, then this technique isn't necessarily going to give us the most accurate result. The technology will certainly be able to be used, and it can be used as an exploratory technique, but we will introduce some errors into it. And the reason is because we're not reforming the stiffness matrix. The stiffness matrix is held constant throughout the simulation based on the original eigenvalues of the system. So this is really our workhorse technology here. This is used all the time, and it's used in lots and lots of different industries. And there are applications where it breaks down because of the assumptions that the structure is linear. And in that case, we need to move to a different solution. And that solution is what we call directly coupled fluid structure interaction, or DCFSI. Using DCFSI, the two codes, meaning the CFD code and the structural code, will actually communicate at runtime. So using DCFSI, we're running two applications. We're running AcuSolve, and then we're running a structural solver. So AcuSolve and Radios would both be running. They could be running on different machines, and then they would be passing information back and forth to each other. So AcuSolve computes the loads on the structure, and then passes that loading information to Radios. Radios then performs its part of the computation, computes the displacement, and passes those displacements back to AcuSolve. AcuSolve then displaces the mesh and performs another calculation of the response of the flow to that motion of the mesh. And the two codes communicate in that fashion, and they continue in that fashion throughout the duration of the simulation. The strengths of this technology are that you can cover really any type of application that your structural code can handle. So in terms of nonlinearities, in terms of contact, all of that is supported as long as the structural application supports it. So this really opens up a more broader application area for doing these FSI simulations. Of course, the downside of doing the DCFSI is that it's a little bit more effort because you have to build the separate structural model and separate CFD model, and you have to maintain both of them and ensure that they're going to be functioning properly during the simulation. And then also there's a little bit more computational overhead because we are running the CFD solver, and then as the CFD solver waits for the structural solver, there's additional runtime associated with that. And then when the structural solver is done and the CFD solver is running, the structural solver is just kind of sitting there waiting. But for a lot of applications, this is definitely the way to go, and we've had great success with it. You can see here some animations of a subsea pipeline that's undergoing deformation as a result of subsea currents inducing vortex shedding on the pipe, which gives rise to oscillating loads, and then that causes things to deform. The reason that this was done using the DCFSI technology is because this pipe is actually embedded in mud, and that introduces some nonlinearity into the system. That's the technology that we have available. And now it's time to start talking a little bit about how we actually utilize this technology and how we can incorporate it into our simulation approaches. The demonstration that I'm going to give in a couple of minutes is based on AcuConsole as our graphical user interface for setting up and running the simulations. So AcuConsole has a number of benefits. CAD associativity is one of them. This is a very, very powerful tool for doing parametric analyses and for doing simulation-based design in general. In addition to that, AcuConsole has CAE automation capabilities through Python. So we can set up these fairly complex fluid structure interaction simulations in a fully automatic fashion by running a Python script to accomplish that. AcuConsole also features fully automatic mesh generation with a lot of different advanced features. And we'll see a few of those advanced features in action when we start doing the demo. Also, AcuConsole was built for CFD. It easily handles very large models. I've opened models on the order of 500 million elements before in the graphical user interface, and had fairly interactive frame rates. So I was actually able to rotate it and spin it and scale it and zoom it without any problems. So the demonstration case that we're going to look at came to me on the drive to work a few months ago. I live in upstate New York, and the weather is not necessarily good in the springtime here. But I was driving to work, and there was a pretty bad windstorm and rainstorm. And I was on the highway, and I looked over at the side of the highway, and I saw this road sign that was bending and twisting and just flapping in the wind. And I thought, hey, that's a fantastic application of fluid structure interaction. So I kind of sat on it for a while and was trying to come up with a reason that I could actually work on it and build a model of this thing so that I could see how the simulation looked. And this happened to be my opportunity to do that. So what we're going to be looking at is a yield sign that's being subjected to a very high wind condition. And we're going to look at how that yield sign responds and how the fluid structure interaction takes place. So just to give a little bit of detail about the process that is going to be used to develop this demo, the geometry was constructed using SolidWorks, which is a commercially available CAD package. The structural model was built using HyperMesh, and the CFD model is built using AcuConsole. We're going to be using the practical fluid structure interaction technology. We could also use the directly coupled fluid structure interaction technology. But we're gonna focus on the PFSI aspect in this webinar. I do have the DCFSI model as well, and if we want to turn that into a different webinar, we certainly can. So with that, I'm actually going to get started on the demo now. And our starting point for the demo is going to be HyperMesh. So I've got HyperMesh opened here, and we're going to load up the Radios bulk data user profile. And then I'm going to import an existing HyperMesh model. So I have this road sign model. I'm going to open that up. And what you can see is that I have this yield sign generated as a shell model in HyperMesh. So if I rotate it a little bit, you can see that we use the mid-surface capabilities to generate both the sign as well as the post. So the sign, the material that we're applying for that is aluminum. And then for the post, again, we just have this one layer of mid-surface shells. And the material model we're using for that is steel. Our goal on the structural model, because we are using PFSI, is to just get the mode shapes and the eigenvalues of the system. So in order to accomplish that, we don't need to apply any loading. All we need to do is apply the proper constraints. So we're not going to get real fancy with our constraints. What I've done here is constrained the nodes at the base of the sign to be fixed in all directions. So we're assuming that this thing is in rigid contact with the ground. We're not going to model any type of soil motion or soil resistance or anything like that. And then we're going to set up our simulation to compute the first, I think, 20 modes is all I set this up for. And there is no limit on the number of modes that we can include when we're doing this analysis using AcuSolve. We can include as many as we want. For the most part, there's no need to include more than, say, 10 or 20 modes. Most of the energy is associated with those lower modes. So again, there's no limit, but for this application, I just arbitrarily chose 20. So with that, we can actually go ahead and run the model. So again, I've already set this up appropriately to run Radios. So I can click on my Radios button, and now I'm launching the structural solver. So this analysis is fairly quick. It's only going to take about 20 or 30 seconds to run through this. It's a fairly small model. But once the analysis is done, it'll produce an OP2 file as we requested in the input settings. And that OP2 file contains all the information that we need regarding the eigenvalues and the eigenvectors. So the analysis is now done, and we can open up our structural model results in Hyperview, and we can visualize them just like any other structural model. So here I have the road sign model loaded into Hyperview, and I have my animation mode set to modal animation. I've reduced my scale factors a little bit so that we can get an indication of what this looks like. So we can animate the different modes. So there's our first mode. Our second mode is this kind of what will end up being our streamwise direction. We can see the road sign moving back and forth. And the third mode is a kind of a combination of the twisting as well as a little bit of streamwise deformation. And we could continue sweeping through all these different modes to investigate our structural model. But we're going to assume that our structural model is correct here, and we're going to jump into the next part of this analysis. So now we've completed our structural model, and we're going to jump into the CFD side of things. So I'm going to use my terminal window to launch AcuConsole, and I'm going to have it create a new database called road sign. So the model is now opened up, and I have my blank database here. And the first step that I'm going to do is import the geometry. So I'm going to import a parasolid file. So I'm going to set my file filter to be parasolid. And then I'm going to go into my SolidWorks directory, and I'm going to open up the fluid volume of this model. And the first thing that AcuConsole does is interrogate that CAD model a little bit and return some information to me. It tells me what the geometry size is, and then it also gives me options on how I want to group the model. Now, in SolidWorks, I applied names to these different faces that are going to be important for my analysis. And that allows me to retain a grouping by those face names when I import my model into AcuConsole. So the way that AcuConsole handles this is a feature called grouping by attributes. And the name of the attribute is SDL/Tyson name. So that's the attribute that I'm going to be telling AcuConsole to group the items by. So I'm going to click on OK. And once I click on OK, it actually reads in the CAD model. And it's also detecting all of those different attributes that were set on the faces. So once I get control of the screen back and the CAD model's been imported, I can expand my surfaces, and you can see that I already have these group names present. And these group names are corresponding with the different CAD faces in the model. So what we're looking at now is the far field boundary. So this is my outer bounding domain. And I'm going to set my display type to solid and outline. And then I'm going to turn the transparency on. And once I turn on transparency, we can see inside the model here. And you can see that we have this road sign embedded within the outer bounding volume, which is just a cylinder. And if I start toggling off some of these different faces, I'll toggle off this far field, I'll toggle off the top, and I'll toggle off the ground. So there you can see that because we grouped it by that attribute that we assigned to SolidWorks, all of our grouping is actually done for us. So we don't need to do any work to regroup the model. So this is a very powerful feature. The more complex the CAD model, the more beneficial this feature is. So at this point, we're actually ready to go through and start setting up our model. So I'm going to do just a few cleanup things here. I'm going to rename my volume to fluid. And this is we didn't assign any attribute to the fluid volume in SolidWorks, so that's why I just came in as kind of a default name here. And now we've got everything set up the way that I like it. So the first step that I'm going to take is actually importing the structural model. Before we start setting up our CFD simulation, I'm going to focus a little bit on the structural model first. So there's a couple of things that we need to take into consideration when doing a fluid structure interaction. One is that we try to match the physics of the problem as best as we can. And one of the common areas that people run into problems is that they provide an impulsive load onto the structure as a result of the fluid. And that's obviously not realistic. So because we are working in the numerical world, what I typically like to do is slowly ramp the forces onto the structure. And the way we do that is by creating something called a multiplier function. So I'm going to create a multiplier function called force ramp. And then I am going to set it to be just a linear ramp. So I'm going to select piecewise linear. I'm going to select my curve fit values to be my time step. So at time step 1, or time step 0, I don't want any load on the structure. So I'm going to set this multiplier function to 0. At time step 10, I don't want any load on the structure. But at time step 100, I want the full load on the structure. So this multiplier function that I've just created is going to be scaling the forces that are applied from the CFD model onto the structure in the fashion that we've shown here. And what that does is it allows the flow to develop a little bit before we start applying the forces to the structure. And then it also gradually applies the forces to the structure so that we don't have any type of an impulsive load. And now that I've defined that ramping mechanism, we can go to this tool called the Eigenmanager. And this Eigenmanager allows us to import our structural model. So I'm going to create a name for this, and I'm going to call it Radios Results. And then I'm going to import my Nastran OP2 file. And I have that file stored in my Radios bulk directory here. And AcuConsole is now actually reading the structural model results. And it tells us that it found 20 available modes in the structure. And if I go to show, I can actually display the structure overlaid on top of the CFD. And I can also animate it. So I can animate the mode shapes just like we did in Hyperview. And that allows us to make sure that, first off, our CFD model and our structural model are co-located, which is a common problem. People have different coordinate systems or different unit systems. So this helps us to ensure that we have the models set up properly. And we can scroll through the different modes and take a look at them. So I'm actually going to turn that off now. And AcuConsole now has all the information necessary about the structure to apply this information onto the fluid boundary and set up the fluid structure interaction model. So let's go ahead and do that. If I click on transfer and I tell it to create a new flexible body, and a flexible body is the name of the command that AcuSolve uses to import information about a structural model, I'm going to call it my new flexible body, a flexible sine. I'm going to click on OK. And then I'm just going to say OK here. And what it did is it transferred the information about the eigenvalues of the structure and the stiffness of the structure and the damping of the structure into AcuSolve. And the next step is to transfer information about the eigenvectors, which contain the direction and the magnitude of the displacement, onto our CFD model. So I'm going to select these surfaces that are going to be deforming on my CFD model, and I'm going to tell it to transfer, oops, I'm sorry, can't do that. Actually, I have to load my mesh first. So let's do our meshing process first, and then we'll finish the transfer of these loads. So I'm gonna cheat a little bit on the meshing. I'm going to import a bunch of variables that I predefined through our variable manager. And what these variables allow me to do is just kind of store sizes and store information about my mesh. So my global mesh size, my surface mesh size, items like this I've predefined, so I'm cheating a little bit here when it comes to the meshing process. So now I have all these variables available, and I can go through and I can define them in my meshing process. So my global mesh size, I'm going to set to be an absolute size, and I'm going to set it to be equal to that variable that I defined called global mesh size. Oops, and I have to type it correctly, of course. Global mesh size. Having typing problems today. There we go. Okay, so now when it goes to build the mesh, it's going to use that as the global size. I'm going to create some refinement zones in the wake of our sign post, and that's to capture all the vortices and eddies that are going to be created. So the first one that I'm going to create, we're going to call it post wake refinement, and we're going to turn that guy on. By default, it sets a sphere as the refinement, but we're actually going to use a box. So I'm going to set the box length to be, I'm going to start out with the box center. So the box center is 0.45, 0.535, and the z-coordinate is 0. So that moves the center point of the box. Now I have to specify the length. So the length is 1, 1.15, and 0.3. So now we have this box, and I'll turn the transparency on, and we can see that box will provide refined mesh in the wake of that post. So the only thing that remains is we need to set the mesh size for that. So I'm going to set the mesh size to be a function of my global size. And I'm going to set it to be 2 times 10 to the minus 5 times smaller than my global size. So that's going to give us a good deal of refinement. Then I also need to do the same thing for the sign. So I actually want that road sign itself to have some refinement. So I'm going to call this one the sign wake refinement. And again, I'm going to turn the transparency on, and I'm going to set this guy to be a box, and then I have to fill in the box center again. So the box center is going to be 1, 1.6, and 0. And then we have to set the box length. So the box length is going to be 2, 1, and 1.2. And now you can see that we have this region that will capture the wake of the actual sign itself. And again, we'll set the mesh size to be the same as what we set previously. So global mesh size times 2 raised to the minus 5. And that's going to provide us with some pretty refined mesh. The surfaces of the road sign, we will also set some mesh attributes, and I predefined the surface mesh size on that. And we're also going to set a boundary layer flag. So we want to grow boundary layer elements to refine the boundary layer mesh on these surfaces of the sign. So we're going to set our first layer height equal to the variable that I defined. And we're going to tell it to resolve the total layer height, meaning we're going to give it the stretch ratio, the first layer height, and the number of layers. So I have my stretch ratio set to 1.3 in this variable, and I have my number of layers set to 10 in this variable. I'm now going to copy these settings to the rest of the faces of the sign so that I don't have to type them in again. And now you can see that they're automatically copied, and we're ready to work with them. So at this point, our mesh is fully constructed, and our mesh is fully set up, and we can click on the Build Mesh button to launch our mesher. The mesh takes about 2 to 3 minutes to run, so I'm not going to wait for the mesh. So by the magic of webinar demonstrations, I'm going to open up a completed mesh. So I'm just going to read in this .arm file, and that .arm file contains a completed mesh that is in the process of loading now. And we'll just take a quick look at this mesh so that you can see the type of resolution that we're using for an application like this, and get an idea of what some of those different mesh controls that we set are actually doing when we run the mesh here. So now I'm going to change my display type to solid and wire. And here we can see what the surface mesh looks like. And I can also draw, I'm going to turn off those refinement zones. Now I can also draw a cut plane, and that allows us to interrogate the internal portions of the mesh. So I can scale that cut plane, and we can take a look at it. So you can see that we have a nice boundary layer mesh around the surfaces of the sign. We also have a nice smooth stretching of the elements as we move from the boundary layer out into the volume refinement. And if we zoom out a little bit further, you can also see the impact of those volume refinement zones that we created. Okay, so now that I have my mesh loaded, we can go back to the operation that I started earlier, which is transferring the structural information onto our existing mesh. So the step that I had missed earlier was, in order to transfer the eigenvectors onto the boundaries of our CFD model, we actually have to interpolate the eigenvectors onto the nodal positions of the nodes that fall on our wetted surfaces, on our flexible surfaces. And because I didn't have any nodes present, that's why I got that warning message saying, hey, you have to have some mesh loaded. So I can complete this operation now by clicking on transfer, and now I can select my simple boundary conditions and all my surfaces that I want to be flexible. And when I click on OK, AcuConsole is interpolating the eigenvectors from the structural model onto our CFD model. And now that operation is complete, so the structural aspects of our model are completely set up, and the only thing that remains is the finalization of the CFD model. So at this point, setting up the CFD model is very, very basic. So we just have to tell it that we're doing a transient simulation. We're using arbitrary Lagrange Eulerian mesh motion. We're using the BES turbulence model. And then we have to set some information about our solution strategy. We're going to run it for 3,000 time steps. We're going to use an initial time increment of 0.001 seconds, which I've already predefined in this variable called dt. And then we need to go through and set our initial conditions. So I'm going to say x velocity is another variable that I created for the velocity in the x direction. The eddy viscosity is another variable that I created. So that's going to apply those values there. And then we need to go through our boundary conditions. This far field surface is this outer bounding ring. And we need to set that to a far field boundary condition. And again, we have to specify the velocity. And we also need to specify the eddy viscosity for our turbulence variables. We're not going to apply any boundary conditions for the mesh motion, so we're going to freeze that mesh out there. We're not going to allow it to move as the sign moves. The wall, which is the ground, is just a standard wall surface, so we're going to accept the default boundary condition. The sign surfaces are all going to be walls, and they're a special type of wall. They're a flexible wall, and when I transfer the information about the structural model into the CFD side by projecting the eigenvectors, AcuConsole automatically set the proper boundary condition for me. So here we already have information that this is a flexible body. The mesh displacement type is flexible body, and the appropriate flexible body to associate this is that flexible sign that we created. And that boundary condition is already set for all these other sign surfaces. So if I visit another one, you can see that I already have that boundary condition set. And the last boundary condition is this upper surface of our domain, and we're just going to set that to be a slip boundary condition. So we're going to set slip. And at this point, our model is completed and ready to run. So I can click on the Launch AcuSolve button here, and if I clicked on OK, that would actually, we'll go ahead and click on OK. So that's going to write all the input to disk, and I have the option of running the solver toggled off. So right now we have all the information on disk that we need to actually run the solver, and we could go through and run our simulation if we had sufficient time and large enough laptop to do so. So I'm going to jump back into looking at our results now. So I've already loaded up a representative time step. So this is the last time step of the simulation. And using AcuFieldView, we can visualize that. So I'm going to turn on some of our surfaces, and I'm going to display them using the pressure. And I can zoom in, and we can see that we have high pressure on the front of the sign, and that gives rise to deformation of the sign. So you can see that the sign has bowed a little bit, and it started to deform under the action of the fluid loading. And you can also see the pressure imprint on the ground here, indicating that we have a lot of transient flow present. So it appears that we have some vortex shedding present. And if I draw a cut plane in the z direction, and I color it by the velocity magnitude, we'll see very, very clear indication that we have a highly transient flow here with a lot of vortex structure present in the wake. And if I adjust my color map, you can definitely see these distinct vortices that are forming in the wake, and that's giving rise to some unsteady loading on that sign, in addition to this mean loading level the fluid applies to it. And that's just a representative time step. So of course, at each time step, we're going to get a different snapshot of what the flow looks like, and that's going to give rise to to different loads on the sign. So if we were to make a 2D plot of what the displacement looked like at various locations on the sign throughout this simulation, this is what we get. So I've got 3 monitor points included in the simulation. I have 2 that are on either corner of the sign in the upper side, and then 1 that's in the center at the top of the sign. So they're indicated in this image. And then here you can see the plot of the displacement as a function of time. The center post deforms, and then you can see that reflected in the black line in the plot. And that doesn't oscillate a whole lot. So it deforms to some mean position, and then it just oscillates a little bit about that mean position. But the edges of the sign deform a little bit more. So they deform in the streamwise direction, and then they also start to oscillate. And you can see some indication of a little bit of twisting by these out-of-phase displacement curves between the red and the blue lines. And if we take a look at an animation so that we can actually visualize some of this activity that I've been describing, you can see the sign is displacing. And then once it's displaced to some mean level, you'll start to see a little bit of a rotation of the corners of the sign starting. So here you can see they're just flopping around a little bit, and here that oscillation becomes a little bit stronger. And this process will continue as we allow the simulation to run even longer. You'll continue to see this sign oscillating about this mean position that it's displaced to. So that's all I wanted to cover in the time that we have available for this demo. So at this point, I'll turn the presentation over, and we'll move into our concluding steps and wrap up our webinar.
Okay, thank you. Welcome, everybody. We're going to cover a few more applications before we wrap up. So Dave just showed a nice application of AcuSolve and Radios. And again, it's part of the solver neutrality aspects of HyperWorks for analysis. We just wanted to talk about other coupling examples that have been done. And so I just have a couple more slides to go through. So one particularly good example is a validation, actually, of AcuSolve for predicting flutter validation. And this is a project done with MSCMD Nastran to predict the direct coupled motions of this structure. And I know it's a very busy slide. The Mach number on the flow is 0.47, but this is a validation case. And what's very interesting is predicting flutter is a very subtle phenomena to predict, where you perturb the airfoil and then you flow air over it at different flow speeds, and then see if the vibration is going to dampen out or be self-sustaining or go critical and eventually cause the solution to stop. And you'll see on the lower right-hand side, as we perturb the Mach number, at low MAC numbers, we got the red line where the initial perturbation dampened out with time, and then a little bit higher flow speed with the same initial perturbation, and we got a self-sustaining oscillation of the wing, and that's the purple dotted line that continues onward. And then increasing the flow speed a little bit higher to Mach number 0.5, and you'll see the initial perturbation, the vibrations get bigger and bigger, and the solution stops. And this is a white paper that was actually done by Dr. Robert Sambogue of Altair Engineering, and we can provide this to our customers if you'd like to study this case more. Another application done with AcuSolve and Abacus is an unmanned vehicle wing deformation, and this was meant as a quick demonstration and almost a tutorial case. You'll see the geometry on the left we created in SolidWorks, very straightforward, so a very simple aerodynamic body of really a cigar tube, if you will, with a simple NACA airfoil shape. Creating the CFD model and meshing it and setting it up for running an AcuSolve took about 4 hours. And you'll see the animation playing on the right-hand side. I'm just showing that the mesh deformation, the motion of the airfoil does asymptote almost to a steady state with a little bit of a low-frequency vibration. We did mesh it pretty coarsely for the sake of having something we could demonstrate and use for training. Doing the structural response took about 3 hours, and we read 20 mode shapes into the AcuConsole model using the techniques that Dave just showed us. We run a steady state CFD model to get the initial flow field that we use to initialize the transient model. And I think what's pretty neat here is on a desk side engineering workstation, the total elapsed time from start to finish was 28 hours, with about 8 to 10 hours of labor, and the rest of that was running the steady state and transient models. And you'll see we got about a deflection here on a 4-meter long wing of about a half a meter. A couple other interesting applications from automotive. On the left-hand side is a shock absorber problem where the initial pulsating velocity is causing a damper to move up and down. On the right-hand side, we have a model of a door seal, so the volume change due to contact of, say, a door with a door seal, forcing the air out. And this was a simulation that was done with AcuSolve and Abacus, and we modeled the rubber as a hyperelastic material. Final example here is something that was done with the AcuSolve PFSI approach, and in this case, we got the mode shapes from ANSYS, and this was an example of a wastewater treatment plant. The gray just represents isosurface of velocity magnitude, so there's fluid being injected into the problem on the lower bottom side in those little R2D2 units, if you will. And what's significant here is they had some standpipes into the flow field that would inject materials in. And the significant result here was they wanted to look at how much those pipes would vibrate and space them so that they would not vibrate into each other. So they ran an analysis, saw some interference, went back and stiffened the pipe, increased the wall thickness. We ran the ANSYS modal analysis, ran the AcuSolve analysis until they had a very large margin on making sure that the standpipes would not vibrate into each other. Okay, so that completes the overview and demonstration, and now we'll move into the final phase of the presentation. One interesting thing about how we do our licensing in HyperWorks for Multiphysics is in the current version, if you were running, say, AcuSolve and Radios and doing a co-simulation, say you're running an AcuSolve model on 128 cores and Radios on 8, you would do a unit drawer for each solver. Coming in HyperWorks 12 this fall, what we'll do if you're running a multiphysics analysis is we'll look at the aggregate charge of your solvers and just do a drawer equal to that aggregate charge. So we believe this provides more value to our customers and encourages you to perform these type of simulations. Okay, so as a summary, I'd like to thank you for attending our HyperWorks Solvers for Smart Multiphysics. We believe we have the most comprehensive high-end solver offering for a wide range of FSI applications. And again, when we perform these simulations, we try to exhibit the best of scalability, quality, and robustness, our SQR formulations. And then 2 final notes. Please check out our online training material. We have now virtual instructor-led classes as well as self-paced classes If you go to altairhyperworks.com and go to Training Home, you can look at and view some of this material and download it. And then finally, we invite you to attend our next HyperWorks webinar on August 28th. This will be entitled Simulation and Mathematical Modeling with HyperMath, 2 p.m. Eastern Standard Time in the U.S., New York or Detroit time. And it will be a 45-minute introductory webinar demonstrating how HyperMath is helping engineers to develop and perform mathematical operations on various types of data, including data associated with CAE pre- and post-processing.